Among non-financial drivers, geopolitical risk now dictates market performance. The connective tissue of international trade is highly sensitive to state actors. Traditionally, the investment industry handles this through discretionary macro. This approach relies on qualitative analysis, attempting to anticipate the individual political agency of leaders driving sudden trade volatility or policy shifts. The problem with this discretionary approach is that it often reads like op-ed commentary. It lacks the mathematical depth required to map complex statecraft into actionable quantitative portfolio inputs. On the other end of the spectrum is systematic macro, an approach that attempts to bypass qualitative human opinions entirely. It relies purely on historical data and rigid time series models to execute trades. But systematic macro has a fatal flaw. It struggles to process strategic human agency. A sudden structural shift, like an unexpected trade embargo or military action, does not always have a clean historical precedent for a model to reference. This leaves the industry with a severe analytical gap. On one side, unstructured geopolitical opinions, and on the other, rigid econometrics blind to political strategy. Solving this requires a hybrid discipline known as computational global macro. It subjects human strategic interaction to rigorous mathematical bounds, making geopolitical risk quantifiable. Standard game theory assumes players are perfectly rational agents, acting solely to maximize absolute wealth. In international relations, that assumption collapses. States routinely ignore optimal economic choices to optimize for non-financial commitments, like territorial security or ideological dominance. Real political actors also face tight timelines and severe cognitive limits. Economist Herbert Simon defined this reality as bounded rationality. Because leaders cannot compute every possible future scenario, they operate as satisficers, decision-makers who accept the first option that is simply good enough to meet their immediate constraints, rather than holding out for a globally optimal result. This chart shows two competing states, illustrating a concept known as maximizing difference. A boundedly rational state will intentionally sacrifice its own absolute economic gains, provided the decision causes a more severe deterioration in their rival's position. To model geopolitical risk accurately, quantitative analysts must discard simple profit maximization. We have to construct utility functions that account for bounded logic and the pursuit of relative power. We can begin to build these utility functions using an attack-defense game, which serves as a proxy for physical conflicts or trade negotiations. Think of this standoff like a football game. We divide the actors into offense, seeking to change the status quo, and defense, preserving it. This matrix outlines actions. Offense chooses run or pass. Defense defends run or pass. If offense passes and defense wrongly expects a run, offense secures 10, defense takes -10. With perfect information, a zero-sum equilibrium is reached. Successfully predicted plays yield zero advantage. While this matrix clearly defines the mechanics of conflict, it is useless for real-world geopolitics. It assumes complete information, a luxury that state actors never possess. Statecraft is conducted through games of incomplete information. You rarely know the true strength or hidden capability of your adversary. Bayesian probability addresses this by introducing a player's type. A type is a hidden variable that dictates an adversary's true underlying payoff matrix. This second matrix represents a weak passer type, characterizing an opponent whose infrastructure is compromised. Notice the payout margins. Here, the attacker faces higher risk. If defense predicts a pass, offense sustains heavier damage than the defense itself. Before committing to an action, the offense must now assign probabilities to the hidden state of the world. Are they facing a strong type or a weak type? Predicting state action requires calculating probability-weighted average payoffs across these multiple unknown contexts. That is a computationally intense problem demanding an algorithmic solution. We map this problem into a machine learning framework using contextual multi-armed bandits, or CMAP. In this framework, the strategic actions, such as running or passing, become the bandit's arms. The Bayesian types representing opponent's strength become the contexts. The algorithm's job is to solve a core tension, balancing the exploitation of known successful strategies against the exploration of unknown options. This equation is the upper confidence bound algorithm. The first half tracks the average real-valued payoff of an action, driving exploitation. The second half represents the confidence interval, forcing exploration. It mathematically compels the model to test actions based on infrequent utilization. By running this algorithm, we can simulate exactly how an intelligent geopolitical agent learns to act optimally under the fog of incomplete information. To see this in practice, we set the parameters for a simulation run of 105 iterations, assigning a 30% probability that the adversary is a strong passer type. This line graph shows the simulation results, tracking the average payoff of the run strategy against the pass strategy over time. In the early iterations, a paradox emerges. The pass strategy yields a higher initial payoff, driven by its massive absolute upside when facing a strong context. But just after 101 iterations, a critical crossover occurs. The algorithm forces a strategic pivot, and the run line permanently breaks above the pass line. This occurs because, over a long enough timeline, the probability weight of facing a weak type neutralizes the high absolute payout of a strong type. The model mathematically proves the slower, safer run strategy is optimal. In quantitative modeling, we use sensitivity analysis to ensure that minor shifts in our input probabilities do not cause the entire logic structure to disintegrate. This updated chart shows the results when we alter the core parameter, increasing the probability of facing a strong passer type from 30 up to 40%. This adjustment introduces immediate volatility into the early phase of the simulation. The relative trajectories of the two strategies drastically fluctuate as the algorithm recalibrates. Yet, as the iterations continue, the noise settles. The run strategy successfully reestablishes its long-term dominance. This stabilization proves the underlying structure of the game is robust. It filters out early volatility to provide portfolio managers with a high-confidence directional signal. The algorithm's iterations represent actual units of time. In real-world geopolitical standoffs, these are the months and years required for a strategic posture to unfold. By applying this mathematical framework to physical flashpoints, from escalating trade tariffs to border disputes, funds can pre-calculate the ultimate equilibrium point of a conflict. Equipping systematic managers with a calculated directional view of conflict provides a distinct analytical edge over strategies built entirely on qualitative reactions to daily headlines. Computational global macro proves that by mathematically binding agent preferences, Bayesian tights, and reinforcement learning, geopolitical risk is integrated directly into the optimization engine.